Hello there, Physics 1 class. It's episode 3, and we are going to get into chapter 1 today. We're going to be getting into the chapter so that you can do the homework. The homework is due coming up here, and so we want to get started as quickly as possible. So I'm going to switch over to the PowerPoint, and we will get all right. So the first question is from the reading. What is the difference between speed and velocity? This is an important distinction because usually you deal with speed when you're driving in your car and you look at the speedometer. That is your speed, not your velocity. Velocity is a vector, and so we need to talk about what the difference is between a speed and a velocity. So let me switch over to my hand, but let's read the answers here. Okay, so speed is an average quantity, while velocity is not. That could be true, but sounds a little strange. Could it be B, velocity contains information about the direction and motion, while speed does not? No, that part is true. Velocity does contain information about the direction. Speed is measured in miles per hour, while velocity is measured in meters per second. That's not true. We could have speed in any units we wanted to. We just miles per hour is kind of arbitrary. The concept of speed applies only to objects that are neither speeding up nor slowing down, while velocity applies to every kind of motion. Or E, speed is used to measure how fast an object is moving in a straight line, while velocity is used for objects moving along a curved path. So it's B, velocity contains information about the direction, while speed does not. So strictly speaking, that is true. Okay, so I will use the example of a wolf spider. Wolf spiders are very fast, and I have a lot of them by my house, and they come in sometime. So let's say we have our wolf spider here, and our wolf spider, we want to know what its average velocity is. Well, if the wolf spider's moving all over the place, right, and here's our wolf spider, he's big and kind of scary looking. He's moving this way. Actually, that kind of looks like a bed bug, not a wolf spider, but whatever. So if he's moving this way, his speed is going this way. So whatever direction he's moving, I draw a line here, that is going to be the direction of his speed. And his speed is changing directions all the time. Speed's not a velocity, it's a scalar. But if we drew his velocity, we would start at the origin, wherever that was, and then we would draw a straight line out here. And the velocity is the distance between our origin and over here. That's the magnitude, but it also has a direction. So here's our angle here. So if we have a velocity, we need to also have a direction. Speed doesn't have a direction. When you're driving in your car and you look at the speedometer, it just tells you you're going 35 miles an hour. It doesn't tell you where you're going from. And so your velocity is much different than your speed. And your speedometer is a good example of that. Okay, so let's go back here. All right. So moving on. The quantity 2.67 times 10 to the 3 has how many significant figures? So this is important because when you are multiplying two quantities together, you need to decide how much accuracy you have. So if you're given a number like this, that means that there are 3 significant digits. So we count the first the first number and then the second two, and that would tell us that there are 3 significant digits. If we multiplied this together by another number that also had 3 significant digits, we might get more digits, but that doesn't mean necessarily that it's more accurate. Well, it doesn't mean that it's more accurate. So let's look at an example here. So I can have 2.67 times 10 to the power of 3. Then I will multiply this by another number, let's say 3.14 times 10 to the power of 3. And if I multiply these together, I get a number here with 6 digits. So 8.3838, right? And since I started with 3 significant digits in each number, then the most that I can have is only 3 digits. You can only have as many significant digits as the lowest number. So if I were writing this correctly and I were putting it into the homework, I would want to write 8.38 times 10 to the 6. That would be the correct answer. So let's grab this over here and we'll do another example. Let's say now we only have two digits here on this one. So there's 2 significant digits and 3 significant digits here. If we multiply these together, then we get a number 8.277 times 10 to the 6. Well, this does not mean that we are more precise somehow. Now we have to say, well, we only had 2 significant digits up here, so the most I could have is 2 significant digits. So if we wrote this number out, the correct answer would be 8.3 times 10 to the 6. So you see what I did? I rounded off here. I had 277 and I rounded off to the nearest significant digit. So that would be 8.3. I have 2 significant digits and I have to round that off there. And if you're curious about what this thing is behind me, this is a distant galaxy that was captured by the Hubble Space Telescope. And it is called UGC 2885. And going across here, across the galaxy, is 65 million light years across. And what's really interesting is that human beings and all living creatures, the matter in our body, was actually created by stars exploding, because heavy elements can only come when a star dies and explodes. And it probably has to happen several times to get some of the heavier elements in our body. So life as we know it on Earth would not be possible unless we had stars that exploded several times and created these heavy elements. So literally, we're all made out of stardust. Okay, so let's take a look here at this problem. The correct SI units for distance and mass are A, feet and pounds. That's interesting. We like to use feet and pounds here in America. Or is it B, centimeters and grams? Or C, meters and grams? Or D, meters and kilograms? So hopefully you've read the book by now and we know the answer for this. Well, the first one is in feet and pounds. That is an American unit, and it is not an SI unit. Centimeters and grams, those are the metric system, but the accepted answer is meters and kilograms, so 1,000 grams. And a meter, in case you don't know, a meter is about equal to a yard. So if you watch the video A good way to estimate 1 meter is 1 yard. They're only different by 3 inches. So 1 meter equals 1 yard. How much is a kilogram? Kilogram is 2.5 pounds, roughly. It's close. So think a meter is 3 feet. A kilogram is 2.5 pounds. Okay. So just a good way to kind of start thinking in meters. So meters and kilograms. Okay. So let's look at this problem. If Sam walks 100 meters to the right, then 200 meters to the left, his net displacement vector is A, it points to the right, B, points to the left, or C, has 0 length, or D, cannot tell without more information. Okay, well, first of all, we know that he went to the right 100 meters and came back to the left 200 meters. So the displacement definitely can't be 0 because he walked one way 100 meters and walked back the other way. Let's draw a picture. So first it says Sam walked 100 meters over here. So we got to draw 100. Using my drawing pad. He walks to the right 100 meters. Then he walks back to the left 200 meters. So he goes this way 200 meters. That's about a meter. Okay. So, and if you want to know how many feet that is, it's 300 feet roughly. And so it looks like his net displacement is 100 meters to the left. So the displacement is going to point to the left. Let's see what the survey says. Yes, it's pointing to the left. We've done it. Great. Okay, a velocity vector points in the same direction as the displacement vectors. Sometimes in the opposite direction as the displacement vector. Could be sometimes perpendicular to the displacement vector in the same direction as the acceleration vector, or velocity is not represented by a vector. So which one could it be? In the same direction as the displacement vector. So if we started off at the origin, then we started moving, then the velocity vector would be in the same direction as the displacement vector. Okay, so let's draw a diagram of that. All right, so if we start off right here, and here's our x-axis and our y-axis, call this x, and we'll say this one is y. Then, if we start off here, moving, say, in this direction, then our displacement vector is going to be going in this direction, and our velocity vector is also going to be in that direction. Okay, so velocity would be going this way, and then our displacement would be this way. Let's talk about motion. All living systems move, or many of them, at least animals do. And so if we want to understand an animal like a whale or a sea lion, then we're going to need to have some way to talk about motion. For example, scientists are often concerned about how much energy does a sea lion or a whale expend while it's swimming, because that has an effect on its size and also what kind of food that it eats. One example is a study that was done by one of my colleagues here at SLU. They looked at how much energy do sea lions use when swimming. They attached to a sea lion one of these harnesses, and then the harness could track depth and also acceleration and velocity. So as the sea lion was swimming through the water, they could record this data with an electronic device. This device would send information back to the boat, and then they could get acceleration as a function of time. So you see these spikes here? Every time that the sea lion would use one of its flippers, it would shoot forward, and there'd be a sudden burst in acceleration. And they could also get the speed. So here you can see the speed of the boat is this constant line, and the sea lion was swimming at 2.36 meters per second squared. So by getting its speed and calculating the sea lion's coefficient of drag, they could tell how much energy that sea lion would need to eat every day. And based on how much energy it takes to swim at a constant rate like that, then they can tell something about how it eats. So you might know, well, a sea lion would have to eat this much energy a day, this many fish, just to survive. So here, this TF, that is the time between it kicking its flippers. And then in between here, this is the glide time. So they could see how long a sea lion is actually gliding. And from that, they could calculate its drag and how much energy it would take to swim. So this is one example of how physicists can aid biologists in their study of nature. Using these devices, they looked at 4 different sea lions, and they were able to calculate the drag on each of those sea lions. And they found that was pretty similar. But this was important data for understanding how much energy it takes for the sea lion to be able to swim. Once they had the coefficient of drag, they were able to look at what was the metabolic expenditure of the sea lion as a function of the boat's speed. So you see right down here at the bottom, there's a minimum at about 1.4 meters per second. This is the absolute minimum where the sea lion uses the least amount of energy. This is metabolic expenditures, which is watts per kilogram. So based on the mass of the animal, they could tell what was the optimal speed, and it was right about here. So if the boat was going higher, then it would use much more energy. But you see right here, there's a minimum. So that's important because this metabolic expenditure is related to the size, because it turns out that the size of the animal plays a very important role in how much energy it has to expend. And this is something that basically controls the size of animals. So the blue whales, sea lions, the size of those animals is all determined by physics. And that all is But in order to understand how to do this and study animals, we're going to have to come up with a way to talk about motion. And that's something in physics that we're really, really good at. So what is motion? Motion is the change in an object's orientation or position with time. So for example, if you have a motorcycle here, that's going to change over time. And whether or not the motion is constant, that's going to be really important. So if you have a projectile here, you can see that when you throw a ball up in the air, at first it moves really quickly, but then at the end, up here at the top, it starts to move a little bit slower. And this is a really useful diagram that we're going to look at later. So the path along which an object moved is called the object's trajectory. Let's look at an example of motion and how to make a motion diagram. So here we have a skateboarder moving in a straight line. And we see that if we were filming him, there would be frames of him evenly spaced. Here's an example of a basketball. So you see the basketball moves, and as it moves, the distance this direction is the same. So if I draw a line here through my basketball, then each of those distances in the x direction is the same. So this is an example of motion. The distance between these two lines doesn't change. So what that means is, just from this video, we can say that the x motion of a particle does not change. Now let's look at the y motion. Okay, so as we go to the y motion, we see it starts off down here, then it goes to this next one. So if we look at the distance between these two, and we compare it to the next one, we can see that the distance is getting a little bit shorter, and especially right here. If we draw this one here, and through the center of this one here, we see that the distance there is very small. So that means that as we get higher and higher, the velocity is slowing down. Just like when you're at the top of something, then you see that it gets slower and slower. And let me throw something up in the air here. Hopefully we can see it. Oh, there we go. Oh, let me turn off my virtual background. All right, so as I throw this bottle up in the air, no, Sarah, okay. So as I throw it up in the air, and I'll get it right, try not to make it spin. Oh, the bottle stops up at the top. Let's see what else I can throw. So my mouse, so right at the top, it appears to kind of stop just for a second and hang there. So here for cars, we have a motion diagram, and we want to know what's going on in this picture. So my motion diagrams are made for two cars. Both have the same time interval between photos. Which car, A or B, is going slower? Well, let's take a look here. Here, distance between this one and this one is about that far. And if we draw the distance between this car and this car, it's much bigger. So it looks like between photos, the yellow car has moved more than the red car. So we can say that the red car is moving faster. No, the yellow car is moving faster. Red car, no, the red car is moving faster. Wait. Oh, the problem is which car, A or B, is going slower? And it is the red car, because much more, the yellow car moved much more than the red car. All right. So moving on, models and modeling. Models simplify nature, but still capture the essence of what we want to study. We use many models in our study, and there's going to be two types of models that we'll use. Descriptive models, which describe the property in simplest terms, or explanatory models. Models with predictive power based on the laws of physics. And a particle model will be a key to start our study of physics. So what do we mean by a particle model? Well, in the video here, if we, instead of cars, we replace the car by a dot, then we could look at the position of these dots as a function of time. And we would see that as the car is slowing down, then the dots get closer and closer together, slowing down. So let's try and make these marks ourselves, and we will see what happens. There he's starting, gets going, and then as time goes on, then here he's entering the constant motion phase. So at the beginning, the marks are closer together, and I did my best to time it. Let's try that one more time. So we start off right here. Let's try that again. Here we go. Okay. So he starts running, and as time's going on, there we go. And this is tricky. And we did it. So right here at the beginning, the marks are really, really close together. So we have a distance like that, then another distance right here. So as these marks are getting farther and farther apart, that distance is longer. That means he's covering more ground in during that time interval. So this is clearly a case of acceleration. So if I measure the distance here, these marks are much farther apart than at the beginning. And I was a little bit off here. And this also represents something else that you should be aware of. So I've had my phone here, and I had a timer on. And so as the clock changed on my timer, I was making a mark. And since I am a human, well, it's hard to make those marks, look at the screen, and do it every second. So let's take a look here at what this means, because this is a great example to talk about uncertainty. Okay, so these marks appear to be pretty uniform, but there is some uncertainty here in these marks. So a second could have been here. I try to do it every second, but I was definitely off. And so I'm going to put these little bars here, and these bars are going to call my margin of error, or the uncertainty in my measurement, because I could have been off here by at least this much right there. So this is the uncertainty in my measurement, and every measurement that you do is going to have some uncertainty. But in general, we can say overall that it was we believe it, and we do show an example of acceleration. So if I were trying to get a measurement in this, I'd say that my uncertainty between each second was probably off by plus or minus 0.2 seconds, and I'm being pretty generous. Okay, so that means if I were trying to calculate something like this, there'd be at least plus or minus 0.2 seconds where I was off, because it was really hard to do that. So my significant figures, I would say, in this are basically 1. So I have no significant figures, because it was hard to do that. I'm not gonna lie. Okay, so we made our own motion diagram, which was pretty cool. In the video here, of course, there are better ways to do this. So the authors of the book, well, they make it really simple here, and they basically say that there's no uncertainty, but every measurement has uncertainty. But the main thing is here, the same amount of time elapses between each frame and the next, but a single dot is used to represent the object. So the number shows the order in which the frames were taken. So I kind of made my own motion diagram, but as the car is slowing down, these dots get closer together. All right, so two runners are jog along a track, The position are shown as 1 interval seconds. Which runner is moving faster? Well, if we look at our chart over here, it looks like if we start right here, runner A is definitely going faster because if my axis over here is distance, he covers more distance in that 1 second interval than runner B. So runner A is clearly going faster in the picture. And so this is a motion. We've made a model, which is a point. And instead of showing each of those runners, now we just have we have dots.